on extreme values of functions. So whenever you hear extreme values, it means just the maximum and the minimum. Okay, so I have this little graph that I sketched out for you guys. And I have all the different possibilities that you could see on a graph up here. So everybody look at them. So if you look at the point on the left where it says no max, why do you guys think that there's not a maximum at that point? There's no actual point, right, first of all, right? So that would be why it's no max. Now it's okay that it doesn't go like down again on the left side. That's kind of what like Nick was saying. Oh, it's not like a hill. You can still have a maximum on an end point, but you would have to have the point there. So then this next one is a local max. So local means that in that general location, it's the highest point. But it's not the highest point on the whole graph. Do we see this? Phil, you with me? Spacing out. All right, so same thing here. There's no min there because there's not actually a point, but this would be a local max. So in that general area, if I kind of zoom in, that is the highest point. This one is a critical point, meaning that its slope is equal to 0 there, but it's not a maximum or minimum. So sometimes that happens. We can have a slope equal to 0, but not necessarily a max or min. Okay, so there's lots of things in this graph. Okay, so it says a function has an absolute max if it is the greatest y value for the whole thing. So in this case, we do have one absolute max. Do you guys see it? It's right up here. It's the highest point in all. Sometimes we call that a global max. So if you hear absolute or global, those mean the same thing. But in this case, this graph does not have an absolute min. Do you guys see why? Yeah, it keeps going and going and going. So we don't say that it's like negative infinity or anything. We just say no absolute min. Okay, but it has lots of local mins. So in general locations. So I always say like in Whoville. So think about Dr. Seuss. If you like zoom in on this little tiny area, if you zoom in here, that's like the smallest place in that area, right? Yeah, there could be multiple local maximums, but there's only going to be like one highest y value or one lowest y value. The absolute. So we call all these extrema. So if you hear something where it says like find the extrema of the function, it means find all of the local max and mins and global max and mins, or absolute max and mins. Okay, so let's try one. So it says find the local maxima and minima in the function on the left. Is there an absolute max or an absolute min? So the way that we write this is we say a local max or min occurs at the y value. Okay, so we're going to say a local max of this y value, and then we're going to say at x location. Okay, so a local max and min is a y value because it's how high it goes or how low it goes, right? So the local minima are going to be these 2 points. And so we would say, oh, the local minima is going to be -7, and it happened at x equals -10. And the other local min is going to be -3, and it happened at an x value of 4. Does that make sense? And then the local max is going to be this one. So it's going to be, oh, our highest y value is 9, and it happens when x is equal to -5. So how about absolute? Do we have an absolute min?
Yes.
So we say absolute min of something, and then we say at x equals something. So absolute min of what? Of -7 at x equals -10. And then the absolute max?
There's none.
Right, there's none. Okay, because it goes up forever on the right and left. So question. What if we had a closed interval? So what if this had been an endpoint here and this one had been like an endpoint here? Would we always have to have an absolute max if it was closed? I don't know, think about it. So some of you are saying, well, you know, like maybe I could have something like that. Is there an absolute max on that function?
Yeah.
Yeah, right here. What if I extend it and it's closed still? Yeah, then it'd be here, right? So if it's a closed interval, there has to be an absolute max. Okay. As long as it's, I guess, a continuous function, because I guess you could have something like, or absolute min. So let's say we have this, and then this was an open circle there. There's actually no minimum then. So as long as you have like a continuous function with all those x values, yeah. Okay, so find the maxima and minima, local and absolute, of the following functions. Okay, so what we're going to do is we're going to use our calculus to help us on this. So we're going to find the derivative. So go ahead and find the derivative. So we get 3x squared minus 6x. And we want to find when our derivative is equal to 0. So we're going to go ahead and set it equal to 0. Let me do it on the next line. And I'm going to pull out the common factor of 3x. So I get 2 locations. And we call these critical values. So these are possibilities for maximums and minimums, okay? But they could be other things. So it could be like the x cubed function, like I said before, where it tapers off to a slope of like 0, but it's not a max or a min there, right? So that could be a critical value as well. So we want to know what's happening in this graph. Now, if you guys remember a lot from pre-calculus and algebra 2 on how to graph things, you should know the basic shape of this graph, right? It's an x cubed, so what's it going to look like? Yeah, so Abby's going like this with her finger, right? So she's saying, oh, it's going to look like something like that, okay? So it can either taper off to a slope of 0 and go back up, or it can taper off to a slope of 0, go down, and then go back up. That's what x cubed shapes look like, right? So let's figure out what this one's doing. So if I put my critical values on my number line, so 0 and 2, and then I test in my first derivative, I can decide if my graph is going up, down, up, what it's doing in the first derivative, so if I test it here. So if I try like -1 in here, I'd have a -3 times a negative number, right? Negative times negative is a positive. And then if I try 1 in the first derivative, I'd have 3 times 1 is positive, 1 minus 2 is negative, positive times negative is a negative. And then same thing with 2. So it's going to be positive. So it means this graph is going up, down, and then up. Okay. Now, I know right away that it's going to go up, down, and up. Yeah, Ari, do you have a question?
Yeah, so if let's say it was going to be the regular
Like an x cubed?
it would go like up and then level off at like 0 and then back up.
Yep.
How would you draw that on a number line? Would there be
Okay, so he's asking a good question here, and this is what I was going to mention. So I knew that it was going to go up, down, and up because I only have 2 choices for an x cubed, right? A positive x cubed. Like I said, it's either going up, down, up, or it's tapering off to a slope of 0. Whoops, I kind of made mine go back down, didn't I? And then going up. Okay, it has to do with the number of critical values that you have. If it just tapers off to a slope of 0 and then goes back up, on your number line, you're just going to have like 1 critical value. It would be like positive and positive on each side, so you'd be up and then up again. And at 0, or at whatever point, you would have a slope of 0. Does that make sense? Okay, so when it has 2 critical values like that, you can kind of just draw it in. You can be like, oh, I know this is x cubed, so it's going to do like up, down, up, like something like that, so you can see it. Yeah?
And what if you have like a vertical shift, so that way like your minimum was, so right, that minus and that plus is describing the slope, not its position.
Yeah, it's just talking about the slope. Yeah, so it'd still go up, down, up, even if there's like a vertical shift. All right, so do we have all these maximums and minimums? So let's put it together. So let's say local min of something at x equals, where do we think we have a minimum? At x equals what?
At 2.
2. And then did you plug that in?
Yes.
Yeah, so it's at x equals 2. And so Nick's already a step ahead. He went ahead and plugged in 2, and he saw that it was 2 cubed minus 3 times 2 squared. So we have 8 minus 12, which is -4. So that means the local min occurs at -4. So I could, sketch that point on my graph. I could say, oh, I have a point at 2, -4, and that's going to be the minimum. All right, how about the local max? Yeah, at x equals 0. Do you guys see how we're getting these values at 2 and at 0? Yeah, because it's going up and then down, right? So that has to be a maximum happening at 0. All right, and so we find that. We find f of 0, which is pretty easy. It ends up being 0, right? So local max of 0 at x equals 0. So what this is leading to throughout this chapter is we're going to be graphing things. So you don't have to sketch this out, but here's what we'd have. We'd have at 0, 0, there's a local max. So I know I'd have like a little bump there. And then at x equals 2, y equals -4, I'd have a local min. So I have my little bump there. And then I know my end behavior goes like that. So I can sketch it. Now, was this like something that was revolutionary for us? Were we like, oh my gosh, I had no idea what that graph looked like? No, because we learned about like things like multiplicity, right? In Algebra 2. You should know what that graph looks like. This isn't one that we don't know how to graph. But is this going to lead to things that we really don't know how to graph? Yeah. Are we going to learn how to graph things like that? Yeah. There's going to be weird graphs that we're going to learn about. Okay. So, oh, did we have any absolutes on that one?
No.
Yeah, no absolute max or no absolute min. Okay, so no absolute max or min. What if I said I was on the interval -2 to 5? What do you think I would do if I was on an interval? Would there be an absolute max or min? Yeah, because basically this graph that we would have had here will end wherever that point is and wherever that point is, from -2 to 5, right? And we can find our lowest point between those, okay?
Did you just make up that interval?
Yeah, I just said what if there was an interval there, and that's, we're going to talk about that as well if we have closed
You
intervals.
still have arrows on the end, but there'll be a point at -2 or 5, right?
No, there wouldn't be arrows on the end if I said it was only graphed on that interval. It would like stop. All right, so f of x equals sine of x. Okay, we all know what this graph looks like. You could probably find the maximums and minimums without calculus. Can you guys do that? Do you know it goes up and down and up?
I always forget.
This happens at 2 pi.
Sine starts at the base.
Sine starts at 0, 0.
The
Yeah.
max.
Cosine starts up here at 1. All right, so it looks like this. So I'm going to guess that the maximum is occurring here and the minimum is occurring here, right? So let's see if we could get that with the calculus. So if I have f of x is equal to sine of x, and I take its derivative, my derivative of sine is cosine. So if I set that equal to 0, I'm finding when cosine of x is equal to 0. So with our unit circle, cosine of x is equal to 0. Exactly. Pi over 2, 3 pi over 2. Is that the only locations?
Negative pi over 2.
Negative pi over 2, and so on. So we could write pi over 2 plus 2 pi k, right? Actually, plus pi k. Yeah, that would give all of them, right?
K means like positive or negative.
K means where k is like an integer, so like -1, 2, 3, 4, 1, 2, 3, yeah. Or 0. All right, so we have that. So those are all of our locations of maximums or minimums, but we don't know which one's which. Okay, so then we could do that. We could do like our number line, and we could say, well, I know it's going to be at pi over 2 and 3 pi over 2, but also subtracting pi. So if I subtract 2 pi over 2, right, I get negative pi over 2, and so on. And we kind of have all those values in both directions. And then you can test in the derivative. So you can test in cosine of x. So if we pick a number between negative pi over 2 and pi over 2, that good number would be 0. So what's cosine of 0? It's 1, right? So that would be a positive number. And if I try something between pi over 2 and 3 pi over 2, maybe like pi, cosine of pi is a -1, right? And then something after there, positive. So it goes up, down, which makes sense because it's an oscillating function, right? And it's going to continue that. Make sense? So really just even based on this picture, if you guys know this picture, you can already say what the local maxes and mins are. How high does this go and how low does it go? 1 and negative. Now you're making me write 2, are you? -1.
Correction.
Ugh. All right, so we're going to say absolute but also local max, right? Because those are absolute as well. Of 1 at x equals, so the first one was pi over 2. Do I do plus pi k, plus 2 pi k? What do I do? So I have pi over 2, what else? Plus 2 pi k. I want to add 2 pi in each direction, right? Forever. Because I want to skip over the minimum. And then I'm going to say absolute / local min of -1, and that happened at x equals, I could do either one. You can do 3 pi over 2 or negative pi over 2, it doesn't matter. So let's say I say 3 pi over 2 plus 2 pi k. Does that make sense? All right, so a critical number is a number C in the domain of f such that f prime of C equals 0 or f prime of C does not exist. So sometimes we're going to have things where the derivative doesn't exist, but something important is happening there. Okay, a good idea of that is absolute value of x. Do you guys remember absolute value of x? It looks like this. But my derivative at 0 is undefined. Now, is that a minimum though?
Yes.
Yeah, that's a minimum. So you can have minimums where the slope is undefined. So we have a minimum of 0 at x equals 0. So let's talk about these other graphs. So x cubed. So what was the funny thing about x cubed? Yeah, the slope is equal to 0 here. Slope equals 0, but no max or min. How about x to 1/3? Anybody know what that looks like? Not a cusp quite. It's kind of like x cubed. So it looks like that. Only right here you have a vertical tangent. So your slope is undefined. It's kind of like a rotated x
But if
cube.
you have x to the 1/2, right, that's just like that right part.
X to 1/2 is just that part, yeah. Because you can't take the square root of negative numbers, but you can take the cube root of negative numbers. All right, so the slope is undefined there, and that ends up being a critical value, not because there's a max or min there. There's not, right? But it will end up being important in the second derivative, because we're going to talk about something called concavity, which is, so like x squared is what we call concave up. Do you guys see why we would call that concave up? Because it's kind of like a bowl. It goes upwards, right? So if we have things like this is concave up, and then concave down. Does that make sense? So there's kind of like a turning point called a point of inflection where it changes. So basically the slope is undefined here. That ends up being what we call a point of inflection because it goes from concave up to concave down. Okay, and we'll talk about that in one of the next sections. And then the same thing with x to the 4th. So with x to the 4th, it's kind of like an x squared graph, only it's a little bit more, it looks like more flat between -1 and 1. And that's one where the second derivative is equal to 0 at x equals 0. But that's not really like a critical value. I don't know why I have that in this point, but 12x squared, thank you. And then what did I do? So x equals 0 at 0. Yeah, let's move it on to the thing. I think you already have 5, actually. All right, so that will be an important calculus graph as well. Okay, there's one more calculus graph. Well, there's a couple more. Do you guys remember like 1 over x? Y equals 1 over x. This is a place where your derivative is equal to 0 along the line x equals 0, but there's nothing really important there. It's not creating a max or min or anything. 1 over x squared is another calculus graph, and then the last one is the one that creates that cusp. Y equals x to the 2/3. Good, you guys have been studying your flashcards. Right, and that one is a minimum, right? So the slope is undefined, but there's a min. Oops, min. Probably. One of my favorites. All right, here we go. So find the critical numbers of the following function. So let's go ahead and take the derivative. Did you guys already do this? So our critical numbers occur when our slope is equal to 0 or slope is undefined. Is the slope ever going to be undefined here? No. So we set it equal to 0, and we factor. So we have 3x and x, 1 and 1, and we want our outer and inner to combine to be 2. So we want a positive on the outside and a negative on the inner. So we get two critical values. We get 1/3 and we get -1. Okay, that's all this question is asking for. Just find the critical numbers, so we're good. Now, could we decide if those are maximums or minimums? Sure. And you could really use the shape of the graph to help you, right? The first one would be the -1. That would be where a maximum would occur. And the second one would be the 1/3. Right? Does that make sense? You kind of think about them in order.
On the x-axis.
Yeah, along the x-axis. Yep, okay, so this next one, I would probably, to make this easier to take the derivative, I would multiply the x to the 2/3 in. So what do we get when we do x times x to the 2/3? Yeah, we get x to the 5/3, right? So I'm going to have 2x to the 2/3 minus x to the 5/3. And then I would take the derivative. Just seems easier than doing product rule. So I'm going to have f prime of x equals 4/3 x to the -1/3 minus 5/3 x to the 2/3. Yep. And now it's kind of hard to tell what our critical points are. We can set it equal to 0 and solve. But since we have that like x to the -1/3, I would recommend getting common denominators. So getting it so it's like a fraction. So something over something equals 0 or is undefined. So I'm going to write this as 4 over 3x to the 1/3 minus 5 over 3, and then I have my x to the 2/3 on the top there. And I'm going to get common denominators. So the reason we're doing this is because I'm trying to find when the slope is equal to 0 and also when it's undefined. So if I see it as a fraction, that will help me for the undefined part in particular. Yeah, I'm going to multiply by x to the 1/3 on the top and bottom of that second part. So I'm going to have 4 minus 5x to the first now, right, over 3x to the 1/3. And this is all equal to my f prime of x. So I want to know when f prime of x equals 0 and f prime of x is undefined. So I have 4 minus 5x equals 0. So I get, what, 4/5? And then f prime of x is undefined. Well, that's 3x to the 1/3 equals 0. So at x equals 0, exactly. Does this make sense? So those are two of our critical values. Well, our two critical values, our only critical values. Okay, does this make sense? All right, so let's put this all together. So the extreme value theorem is the one that talks about the closed interval. So it says if f is continuous on a closed interval a to b, then f has to have an absolute max and it has to have an absolute min for some numbers c and d in a to b. Okay, so we have a continuous function, so underline that, and we have a closed interval. So you always want to check this, and the AP test will do this a lot, where it's going to give you things like, you know, y equals x squared, but it would say things like on -2 to 3. You guys know what y equals x squared looks like. Normally it's unbounded. It goes up forever, right? But if I'm only between -2 and 3, do I have an absolute max and an absolute min? Yeah, does that make sense? What would the absolute max be? It'd be 9, right? Tricky. Absolute max is the y value, so 9 add x equals 3. What would the absolute min be? 0 add x equals 0, right? Does this make sense? So we have to consider those endpoints. So I wrote it in bold, I put stars next to it, and I put 2 exclamation points. So it's pretty important. All right. Huh?
For the graph, so for max and for min, it's always the y value.
Yeah. So finding extrema on a closed interval. So it says to find an absolute max or min, we go through the following steps. So we find the critical numbers. We find the values of f at the endpoints. So we find how high it goes on the endpoints. And it says the largest values from 1 and 2 is the absolute max, and the smallest from the is the absolute min. So sometimes we call this like a candidate's test. So I'm going to show you what I mean by candidate's test. Okay, so it says find the absolute extrema of the following function. Use your calculator to sketch and verify. So I'm going to first find f prime of x. So I get 12x cubed minus 12x squared. And I find when it's equal to 0 and when it's undefined. So it's never undefined because I don't have a denominator. But it equals 0 at 0 and 1. So those are critical values. But I know I'm on a closed interval as well. So if I was doing a check with the number line, I would put -1, then I'd be like, oh, 0's to the left of it, then I have 1, and then I have 2. These are all possibilities for maximums and mins. So you can go through that process and you can see when it goes up, down, whatever. Okay? If it's next to the fourth, probably goes down. Well, there's only 3 sections here, so I don't know. Maybe it's doing something. So we don't know what it's doing. Okay, so you can figure out when it goes up, down, and up, and so on. Okay, but we don't have to. Because what's our goal here? We're just trying to find the absolute extrema. So the AP test does this a lot where they call it the candidates test. And they say, well, these are our 4 possibilities for maximums and minimums. Let's just find the y values that go with them. So if we plug in 0 to the original, we get 0. If I plug in 1, I get -1. So how about -1? What do I get? -3. Is it negative? So it'd be negative. No, it would be +3. And then +4, so 7. And then 2, so I get, what, 1648 minus 32. So 16. All right, so what's our absolute max and absolute min? 16 is the absolute max, and -1. right? Okay, so we're going to have absolute max, absolute max of 16 at x equals 2, and absolute min of -1 at x equals 1. Okay, and we know this because we have a continuous function on a closed interval. So it wouldn't hurt to say something like f is continuous, right?
Do you have to write that on a test?
Probably. If you're just going to jump straight to the candidates test, I probably would. All right, so this one.
Or like on an AP test, but we get a question wrong if we didn't write the words.
On the free response, probably, yeah. All right, so here we go. So here we go. So I do 2 minus 3 times 2/3 is 2x to the -1/3. Okay, this one is not differentiable at a certain number, but it's continuous there. What's it not differentiable at? What makes it undefined?
Zero.
Yeah, because it's really like 2 minus 2 over x to the 1/3, right? Do you guys see how 0 makes it undefined? Okay, so that's why I have students get common denominators, so they can see that. So then they write, so this one would multiply by x to the 1/3 over x to the 1/3, right? A little sloppy there, but you know what I'm doing. So I'm going to have 2x to the 1/3 minus 2 all over x to the 1/3. So I do two things. I find when f prime of x is equal to 0, and I find when f prime of x is undefined. So it's undefined when x to the 1/3 equals 0, which is x equals 0. And then f prime of x equals 0 when 2x to the 1/3 minus 2 equals 0. So add the 2 over, divide by 2. Do you guys see what it's going to be? Yeah. 1 cubed, which is 1. All right. So these are our possibilities. These are a couple possibilities for max and min, but we're on a closed interval, right? Okay, so we have numbers. We have -1. So I like to see the number line. I don't know why. -1 to 3. And I have these other critical values of 1 and 0. Are they between there? Yeah, 0 and 1. Sometimes they're not on that interval, so we don't have to test them. So we have -1, 0, 1, and 3. Is that the endpoint? 3. Okay. And then I test. Now, a lot of people think just because we have f prime of x is undefined at x equals 0, they're like, oh, there's going to be like a vertical asymptote there, or there's going to be a hole or something weird. Okay, if I plug in 0 here, does it work? Can I do 0 to the 2/3 power? Yeah, cube root of 0 and then squared is still 0, right? So 0 is a point on that graph. So 0, 0 works. So I have 0, 0. And if I try 1, I get 2 minus 3 is -1. If I try -1, I get -2 minus 3, and then I have the cube root of -1 squared. So see how that's still 1? So I have -2 minus 3 is -5. And then 3 gets a little gross. We can find the decimal version for 3 if we want. So 2 times 3
6.
minus 3, I know that, times 3 to the 2/3. All right, so we get, what, -0.240. So what's our absolute min and absolute max? Yeah, so -5 and 0. So we're going to say absolute max of 0 at x equals 0 and absolute min of -5 at x equals -1. So this is a weird one. This is one that's going to have a cusp. So let's look at the picture. So go ahead and graph it out with me. I'll do it on Grapher so you guys can, well, it's fine. I'll do Grapher. So you guys can do it on your calculator. I thought I was going to have a cusp. I guess not. Hang on. 2 cubes. What do you make up? I feel like I'm missing something. I think there should be a cusp. I don't know why the grapher's not showing it to me. Yeah, there's something over here too. Why is it not showing it to me? What's wrong with you, grapher? It doesn't like it. All right, so anyway, let me do it on this. So what do we have? 2x minus 3. Do you guys all have this? Did you see what it looks like? So there should be a part over here, and then there's going to be like a little cusp. Okay, so that's what the graph looks like. So let's see what it says. So we said there's an absolute max of 0 at x equals 0. So if I made it so I was only on -1 to 3, I think you guys will see that. So if I go to my window and I do -1 to 3, then you can see that 0 is the highest point. Does that make sense? And then this is just a little bit below the axis, I think. Yeah, that -0.240. Okay, does that make sense? Do you guys get it? All right, so it should match up with your graph. All right, so let's do one more. This would be a good one to practice for the derivative, for your midterm thing. Do you guys know how to take the derivative of this? Yeah?
No.
So the derivative of cosine squared is going to be 2 cosine of x times sine of x, right? So if I'm trying to set it equal to 0, I'm going to pull out a 2 cosine of x, the GCF, and I have 1 minus sine of x left. So when I set each piece equal to 0, I get cosine of x equals 0.
Wait, wouldn't it be 2 cosine x plus 2 sine?
Oh, it would be a plus, darn. You got me.
I was right.
I wonder why you guys were looking at me funny.
Let's go.
All right, so we end up getting sine of x equals -1, and I get cosine of x equals 0. So cosine is equal to 0 at pi over 2 and 3 pi over 2. Those are the only locations on 0 to 2 pi, right? And then sine of x is equal to -1 at 3 pi over 2, so we already had that anyway. So again, we have our closed interval, so we're doing this candidates test. So we said, well, we know we have critical values of pi over 2 and 3 pi over 2, but we're on the closed interval 0 to 2 pi. So here are my possibilities for an absolute max and absolute min. So I don't have to find where it's increasing, decreasing, and so on. So if I plug in 0 into the original, 2 times sine of 0 is just 0, and then minus cosine of 0 squared. Cosine of 0 is 1. So I think I get -1. Do you guys agree?
Yeah.
Will I get the same thing for 2 pi? Uh-huh, because 0 and 2 pi are in the same location, right? How about pi over 2? Yeah, we get 2, because we get 2 times 1 and then minus 0, right? And 3 pi over 2? -2, yep. So we're going to have an absolute max of 2 at x equals pi over 2. And I'm going to have an absolute min of -2 at x equals 3 pi over 2. Okay, so does that section make sense? Do you guys get it? We're going to stop there.